Hello, this is Dr. David Kreller of the Department of Chemistry, Georgia Southern University. This video tutorial is about combustion analysis. I've put this together from the students of my course, Principles of Chemistry 1 or Chemistry 1145, the general chemistry course. This is an important topic. So combustion analysis, when do we do these analyses? Well, anytime we have an organic compound whose identity is unknown. Combustion analysis can be performed to help us determine the chemical formula of the unknown substance. And then basically when you know chemical formula, of course, then you know the identity. And we could have an unknown organic substance whose identity we want to determine as part of a forensic investigation, say perhaps some unknown compound remained at the scene of a crime or something. Or perhaps even as a function of research, or as part of a research program. So how does it work? Basically, we put a little bit of the unknown compound into an instrument called an elemental analyzer. That small little sample of our unknown compound undergoes the process of combustion, with some other information being collected and processed, and then the instrument basically tells us the formula, or the ratios in which the elements, say carbon, hydrogen, oxygen, appear. Basically figure out the formula for us. Okay, so let's look in a little closer detail. Here's the schematic of the most important parts of the analyzer. So we start off with some combustion chamber. Maybe it's a furnace, high temperature environment, across which or through which flows a stream of oxygen, O2 gas. It's like a carrier gas, and when combustion of the sample occurs, the products pass through a couple of absorber cartridges. So basically, the combustion of the unknown organic compound produces H2O and CO2 molecules. Well, the H2O and CO2 molecules are initially all mixed in together. This is like a physical separation technique in a way. We get the H2O and CO2 apart from one another via their selective absorption on these specific materials inside the absorption cartridges. And the analysis, as it works then towards figuring out the number of moles of each of these elements, works gravimetrically. So you'll have a change of mass. You'll have an increase in mass of each of these absorbers, that which has selectively absorbed the H2O and that which has absorbed the CO2. And so the change in mass tells us how much of these compounds were produced. Now, why is that important? Because if we have H2O molecules containing H atoms, those H atoms could have only been present in the sample. So the amount of H2O tells us about the amount, or the number of H2O molecules tells us about the number of H atoms. And similarly, the number of CO2 molecules tells us the number of CO2 atoms that were present in the sample. Then we also have to leave the door open for the idea that the compound could have contained oxygen. But the amount of oxygen that's present, or that was present in the compound, is determined kind of indirectly by mass. You have the mass of the carbon and hydrogen, and then whatever mass is not yet accounted for, that is then taken to have been oxygen. So let's look at a specific analysis. Say we take 1 gram of an unknown sample whose chemical formula, we know that it contains carbon, hydrogen, oxygen, but we don't know the subscripts within this formula. Okay, so combustion of 1 gram produces certain masses of the products water and carbon dioxide. And so now the question is, what's the empirical formula of this compound? Let's remember this information: 0.41 grams of H2O and 1.50 grams of CO2. And we're working towards what's the empirical formula. So let's look at some calculations. I've used this table So the first thing we do is for each product determine the number of moles. So for the carbon dioxide, the 1.50 grams will divide by the molecular weight of carbon dioxide molecules. So 0.034 moles of CO2. But we were only using the CO2 produced to get at the carbon that was in the sample. So 0.034 moles of CO2 actually corresponds to 0.034 moles of carbon, because there's one carbon for every CO2. Obviously, it's a one-to-one expression or a relationship. But we'll also determine the mass of that element that was in the sample. We know that there's 0.034 moles, so we'll multiply that by the atomic weight for carbon. 0.408 grams of carbon were in that sample that was combusted. Okay, we'll do the same thing for the H2O which was produced. Remember, the combustion produces CO2 and H2O. So for the H2O, we divide this 0.41 grams by 18.01 grams per mole. Calculate 0.023 moles of water. Product is water. Okay, but we're concerned about the moles, the amount of hydrogen that was in the sample that was combusted. So we have to work in hydrogen. So for every mole of H2O, there's 2 moles of hydrogen. So it's actually the number of moles of hydrogen is 2 times that. And we can figure out the mass of the hydrogen that must have been present in the sample by multiplying the number of moles by the atomic weight for hydrogen. Okay, like we said, we need to know the amount of oxygen, so we can figure out now the mass of oxygen that was present in the sample. 1.0 grams was the total mass that was combusted, and now we know that there was 0.408 grams of carbon and 0.046 grams of hydrogen. So we subtract the sum of those two from 1.0 and we get 0.546 is the mass of oxygen that must have been present in the sample. But for the purposes of the formula, we need to know the moles. We'll work towards a molar ratio. So anyway, 0.546 grams of oxygen divided by 16.00 grams per mole. That's the atomic weight of oxygen. Equals 0.034 moles in that sample. Okay, so we know this compound contains carbon, hydrogen, oxygen. So we take these 3 molar amounts and we plug them into the formula. But of course, a formula, any formula, does not contain, 0.034 atoms of carbon. We have to use this information to generate a formula. So we'll take these 3 numbers and divide them by the lowest of the numbers, 0.034. That will force the lowest of the numbers to be equal to 1. We do that quick calculation. We get carbon, hydrogen 1.36. Well, if you solve enough of these problems, after a while you'll start to realize, you'll start to become familiar with certain values. If something's very close to 1 or 2 to an integer number, it probably, within experimental error, can be safely rounded to that integer. But this is pretty far away from an integer, 1.36 ratio for the hydrogen. But it's pretty close to 1.33, which, if we multiplied that by 3, the 1.33 would become 4, and the carbon and oxygen each become 3. So that's one example calculation, and I'd like to thank you for paying attention to this little video.